Today we are in the middle of Solar Cycle 25, which began in 2019 and will last approximately until 2030, going through cyclical highs and lows of solar flares, coronal mass ejections, and solar storms that will peak this or next year, making this a crucial period of time to invest in solar weather monitoring capabilities. Why it is important to study solar activity. It is no exaggeration to say that solar flares and the geomagnetic storms they can cause have a significant impact on everyone's lives. They can cause failures in the operation of satellites that are crucial for maintaining communications and navigation systems on Earth. They can also damage power grids, leading to massive blackouts and pose radiation risks for astronauts as well as for pilots and passengers of high-altitude flights. Active solar cycles increase the frequency and intensity of solar flares and pose danger to all technology and services affected by space weather. Such disruptions to critical infrastructure can be very costly to the economy of developed nations. Power outages caused by solar activity cost tens of billions of dollars every year. The potential global economic impact of space weather events, such as a severe geomagnetic storm, are significant and could incur losses totaling €38.4 billion, $41.1 billion per day. More than half of these losses are caused by indirect costs related to disruptions in supply chains. Damage from solar events can lead to logistical delays, production downtimes, increased operating costs, shortages of goods, and other problems in international trade. Solar weather forecasting also plays a crucial role in safe and effective space exploration. Without accurate forecasts and predictive analytics, space missions and the astronauts involved would be at risk of exposure to radiation and equipment malfunctions. Existing solutions and future needs. In 2024, space weather monitoring and analysis is conducted mainly through government agencies and scientific organizations. Two of the major suppliers of information are the National Oceanic and Atmospheric Administration in the United States and the European Space Agency. These organizations manage data from various sources that include satellite missions and ground-based observatories in order to create a comprehensive picture of solar activity. In addition, these organizations often use empirical forecasting models that are based on historical data. These models help identify patterns and correlations in space weather phenomena, which can then be used to predict future events. However, this information is not always accurate or up to date, which significantly reduces the relevancy and efficiency of the forecasting. In March 1989, when modern methods for space weather forecasting were not yet available, a powerful geomagnetic storm caused by a solar flare triggered large-scale technological disruptions and outages in the Canadian power grid. Millions of residents and businesses in the province of Quebec were without electricity for 9 hours. Another solar flare in August of the same year caused the Toronto Financial Exchange to stop for 3 hours. The lack of information about space weather can also cause significant damage to satellites and other space systems. For instance, a geomagnetic storm in February 2022 interfered with a Starlink launch, resulting in the company losing 38 out of 49 satellites. Starlink was relying on empirical models to predict atmospheric conditions, but these models had insufficient data and failed to make an accurate estimate of increased atmospheric density during a storm. This led to greater than expected atmospheric resistance and caused the satellites to malfunction. Such events highlight the need to develop efficient systems that can provide accurate and relevant data on solar weather. Unlike Earth weather, space weather is a global phenomenon that impacts the entire planet. Therefore, high-quality forecasting requires the collection and analysis of data from around the world, which can only be achieved through a global approach and comprehensive international cooperation. To make this happen, the first essential step would be the creation of a single, global repository for space weather data, a data lake. This would involve collecting and storing a vast amount of information about solar activity from various sources, such as spacecraft, ground-based observatories, and research centers in different countries. This would help to avoid the fragmentation of data, fill gaps in forecasts, and provide a comprehensive understanding of the state of space weather to everyone who requires it. Another important step towards the development of solar weather monitoring and analysis is the integration of innovative solutions in space infrastructure. At present, most information about space weather comes from large governmental systems and satellite groups that provide fragmented data with big time delays. At the same time, maintaining these systems is a big cost for national economies and involves a significant amount of bureaucracy. This problem can be addressed by introducing small satellite groups launched into low Earth orbit. They would act as a reliable backup for expensive scientific missions and will significantly simplify the process of monitoring solar weather and reduce costs, ensuring continuous data collection and preventing the loss of crucial information about cosmic radiation if the main satellites fail. Today, we at Mission Space are actively working toward this initiative as our teams at Spire Global and Millennium Space Systems. A new era of security and discovery. Space weather monitoring and analytics is not just a matter of scientific research. This is an essential need that could transform humanity's future in space and on Earth. Advances in this field will lead to many new opportunities for human civilization as a whole. Expeditions beyond near-Earth space will become safer and more accessible. Accurate space weather forecasts will allow space agencies to plan deep space missions with minimal risk for astronauts and equipment, opening the way for the exploration of exoplanets and asteroids, including colonization of the Moon and Mars. Such missions are expected to become a regular activity by 2030. Protection of the Earth's infrastructure will be reinforced. By understanding when and how solar storms can affect our planet, we will be able to prevent blackouts that could leave residential areas without electricity and heating, ensure stable mobile communications and internet access, as well as ensure safe air travel by protecting flights from radiation effects of solar storms. This will help humanity protect itself from both minor inconveniences and serious threats to health and safety. The development of the space economy will be incentivized. Reliable protection from the effects of solar weather will make space tourism, extraction of resources, and building of extraterrestrial manufacturing facilities the new reality. As such, SpaceX's plans for the colonization of Mars reflect a long-term vision for the development of the space economy. The establishment of human settlements on the Red Planet would involve not only research and new environments for space accommodation, but also the creation of new economic models for extracting and manufacturing resources from extraterrestrial sources. The potential, viability, and safety of these projects largely depend on a high-quality analysis and prediction of solar weather conditions. So, ladies and gentlemen, that's it for this video. Please like, share, and subscribe to Luminary Cosmos for more this kind of content. There's plenty more to come, and I'll see you in my next one.